Hello, this is Jennifer Martinez, and in this video we are going to discuss the inner product and the length of vectors. So let's first go over what the definition of inner product is. By the way, it's also known as the dot product, which you may have heard of from past classes. So the inner product of u, a vector u, and a vector v in Rn is u dot v. It's going to be equal to the transpose of u times v. And it's the transpose because the definition is u1 v1 plus u2 v2 plus all the way to un vn, as you know from your past classes, which in matrix terms is the transpose of u. So that way this is a 1 by n, and this would be an n by 1. It ends up being a 1 by 1, so it's a scalar. There's many applications that use the dot product or the inner product. And the concepts, geometric concepts of length, distance, and perpendicularity in R2 and R3 are also very well known. So let's look at example 1. Example 1 actually asks you to compute u dot v. So here's u dot v, and by definition we just write u transpose times v. So the transpose of u, right, this column is just going to be a row, and we're going to multiply these together, so we get 2 times 3 plus negative 5 times 2 plus negative 1 times negative 3, which is negative 1. By the way, v dot u, you can see here, is the same thing. If you take the transpose of u times the transpose of v times u, and you transpose this one, you can see here these entries are just switched, since multiplication in the reals is commutative. It turns out that the dot product is commutative as well. It is clear why the dot product is commutative from this example. You can actually prove it. And we also proved it in the past in section 2.1, it says there, using the transpose. But here is all the different properties. So if you let u, v, and w be in Rn, we know that from above that the dot product is commutative. We also know that you can distribute w on the right. You can check that out with the transposes as well. The first three you can just see in chapter 2. The third one says you can bring out the c no matter where the c is. The last one is the one that I want to concentrate on. It says as long as u dot u is greater or equal to 0, what we have is if u dot u, or I should say u dot u is equal to 0, if and only if u is equal to 0. So let's go ahead and show that. So again, if and only if means both ways. So I'm going to start with going this way. If u equals 0, obviously u dot, then u dot u, all or just 0 plus 0, no matter what size it is. So you would have that it's equal to 0 actually. It's not a vector. Going this way, if u dot u is equal to 0, that would give us u1 squared plus u2 squared. Let's just say where u is in Rn is equal to 0. That means because all of them are positive, each ui has to equal 0 for I 1 to n. So therefore u is 0. So this one's a vector, that one's not. So it's all correct. Now let's define the length, or sometimes called the norm of v. It's denoted with 2 straight lines here, and it's defined by the square root of the dot product. So it's going to be v1 squared plus v2 squared, right, the dot product of v dot v, that is. And you also have that the absolute value of the norm is just v dot v. That's another way of looking at it. So we have here that where v, by the way, is any vector in Rn. Note if v is in R2, that is just our distance. That is our length. So let's look at that. If v is on R2, it really doesn't matter where it is. So say it's here. So this would be v1 would be this length. And v2 would be right here, each element. And this would be, we know by the Pythagorean theorem, the square root of v1 squared plus v2 squared, which you can see would be the definition of the length or the norm if you were in R2 up there. So let's go and find the length of this example. So what is the norm of u? It's going to be equal to, whoops, the square root of u1 squared plus u2 squared. You can see it's going to be a scalar. If I square that, I get 9 over 25 plus 16 over 25, which, by the way, is 1. The length is 1. They call this a unit vector. So a vector is called a unit vector when the length is 1. So you can make any vector of length 1, and they call that normalize. So let's look at the next example and read here. To normalize a vector v, you divide it by the absolute value, the length of v, to obtain a unit vector in the direction of v. So u equals v over v, the length of v, is a unit vector in the direction of v. So let's go ahead and normalize this vector. So first what I'm going to do is find the length of v. So that would be equal to the v1 squared plus the v2 squared. So that would be 1 squared plus 2 squared is 4. So square root of 5. So if I take this, if I take v and I divide it by the norm of v, I'm going to get 1 over square root of 5 of 1, 2. Sorry, not 1/2. 1 and 2 each entry. So what we get here is 1 over square root of 2 and 2 over square root of 2. So we've just normalized v. And that is a unit vector in the direction of v. So we can see it's just a multiple of v, so it's in the direction. And if you check it, if you check the length of this, that would be the square root of 1 over square root of 5 plus 2 over square root of 5, which is 1. So that's how you do that. So example 2. Let's do the same thing with a vector in R4. Find the unit vector u in the same direction as v, which means let's normalize v. So we know that that is equal to each component squared, which we know is equal to 1 plus 4 plus 4 plus 0, which is the square root of 9, or 3. So I'm just going to take v and divide it by the length of v, or the norm of v, and we're going to get it. So let's see, we're going to take 1/3 of so there it is. Or you can write it in our normal matrix form, and we can check it. If you don't feel like checking the whole thing, we could check. Another way to check is, since we know that we want to check if this is indeed 1, so I could check and not deal with the square root if this, because this still would be 1. So we know that this, the length or the norm of u, is squared, is u1 squared plus u2 squared, or let's just say u dot u, which is u1 squared plus u2 squared all the way through. So this should be 1/3 squared, which you can see is indeed 1. Another way they could ask is with subspaces. Example 3 says, let W be the subspace of R2. So here's a picture of R2, spanned by this vector. So 2/3, there it is right there. There's the X, calling it Z, but it's really X, I think. 2/3, 1. I think we're going to get Z in a minute. And the span would be that whole line. So that whole line they're calling W. Find a unit vector, Z, that is a basis for W. So the book solution says W consists of all multiples of X. So I wrote here, we know that W is any kx, right? Any multiple where X is equal to that vector. So any non-vector in W is a basis for W. So what they chose is made it a little easier for themselves. 2, 3, they just took a K and multiplied it by, they took K as 3 and multiplied 3 by that X, ended up with Y. So then they want to normalize it so we don't have to end up with a double fraction. If we find the length of the Y, we know it's 2 squared plus 3 squared, which is 13. So the normalization of the vector, they're going to call it Z. Oh, the unit vector Z, that's where Z comes in. I see. That really wasn't Z. This one was the X. Got it now. Okay, so, but anyway, so Z is going to be that 1 over the length of Y times the 2/3, and there it is there. So you don't have to deal with the double fraction. Or you can write it in our ordered pair form of what they started with. And the next definition is on distance. So the distance of U and V in Rn is the length of U minus V. So that is the distance of UV is the actual length. So the length, if you remember, or the norm of U minus V is the double straight lines. And I realize that in Rn, you can't visualize that length in unless it's in R2 or R3, but still is the definition. So that's why it says in R2 and R3, the definition of distance coincides with these two formulas, or this formula, as you can see in the next example. Example 4. Compute the distance between the vectors U and V. So what the book did is they took U minus V first. So that would be the 7, 1 and the 3, 2 in vector and matrix form. And they subtracted them and got 4, negative 1. And then they look for that length, or that norm, which is the square root of the first entry squared plus the second entry squared. And they got square root of 17. That is the distance. To see that, you can see here that here's U and here's V. So minus V is really what I want to add. And we add those, we form a parallelogram. So you can see from here to here is U minus V, or the length, or this blue as well, or the length is U minus V squared. Which, by the way, coincides with our distance formula, if you remember. Here's our distance formula that we used in algebra. And if you subtract, you call this x2, you call this x1, you subtract them, you get the same formula. So it does make sense. So even in R3, R4, right, the distance of two vectors can be called the norm of U minus V. So if we take U minus V, dotted with U minus V, we do end up with our distance formula, U1 minus V1 squared, U2 minus V2 squared, right, each entry, and U3 minus V3